All right, guys, quick set of notes here for number 10, multiprotic acids. Multi, of course, you guys know what that means, many, right, several. And then the root here, P-R-O-T, the proton, right? So what we're talking about are acids that have more than one proton to give off, more than one H plus ion that can dissociate. The one that we have talked about already as a strong acid is sulfuric acid. But now we need to kind of split that hair a little bit and notice that only the first hydrogen in sulfuric acid is strong. So the way that this equilibrium would work, if we have a sample of sulfuric acid, every single sulfuric acid molecule would dissociate by giving off that first H plus, right? Notice the forward arrow here. The first H plus would come off of every single molecule. And so we have our strong acid here, and this would be his conjugate base. Now remember that the conjugate base of a strong acid is so weak that it can't go in reverse, right? It can't take the H plus and make the acid molecule again. But what this one can do, because of that H right there, it could be an acid. And so in a sense, this ion here has some amphoteric properties in the fact that it's the conjugate base created when sulfuric acid loses its first ion, and then it can further dissociate. And of course, strictly speaking, we would have the two equilibrium arrows like that, and it can lose the second hydrogen. Now, that second hydrogen coming off is weak, which means some of these ions will hold on to it, and some of them will give it off. And so we would have a Ka value for this, and it would be an icebox situation to figure out what the true pH of that solution is. We're not going to deal a lot in our treatment of acids with these multiprotic, diprotic here for sulfuric, triprotic for something like phosphoric acid. We're not going to do a lot with that. I just kind of want you to know that they exist. And for other acids that aren't a strong acid for the first one, for the first hydrogen coming off, notice that all of those H's coming off would be considered weak acids. We know that because they are all in equilibrium with each other. Now, if you were to do a titration with a multiprotic acid, you would have kind of another distinctive curve, because you would have the first H plus, and then you would have the equivalence point right here, and then you would have an equivalence point for the second H plus. So it sort of has this two-stepper shape to it, which is indicative of a diprotic acid. You could maybe imagine if we had a triprotic acid, then we might have 3 steps, right? And I made that one go kind of high compared to how tall I drew the plot there. But depending on the nature of the acid and the strength of the conjugate base that it creates, we would have different pHs at those equivalence points. Again, really quick notes here because I just want you to see that this exists. For me, the biggest take-home point for you out of these notes is that as you titrate an acid, the H's come off one at a time, right? So we have steps to show the order that they would come off. And then I would like for you to know that for sulfuric acid, strictly speaking, only the first hydrogen coming off would be considered the strong acid. The second acid coming off of that, the second H plus coming off that, would be weak. So that's all. That's it. Let's keep going.